Hello, quick video on differentiation of polynomials. We might be given some horrible polynomial like this. We may have to differentiate it to find the gradient. And in previous videos we've seen how to do individual powers, and we're going to see here that actually it's relatively simple to do this by breaking it up into its constituent parts. Okay. So in previous videos we proved that if we had a function x to the n, we could differentiate it to find the gradient, and we'd find that that function, that the differential is n times x to the power n minus 1. So that's quite useful, isn't it? And what we can find, and I'll do a little demo to prove it, is that we could break up our polynomial to all the different parts and use that method. Okay, so let's have a go at this polynomial here. I've got a quadratic formula and I've broken it up in colours, different colours, so we can see what happens. Yeah. So if we start at our point here, as we did in the previous video, so the x value is x and the base point, and our y value there is going to be our x squared minus 4x plus 4. That's our bottom point. And then we're going to move along a little h. So our other point is going to be at x plus h, and therefore the y value is going to be the three parts here, the x plus h squared minus 4x plus h, and then plus 4. Yeah. All we've done is substituted x plus h for where there was an x. Okay, so we know what our along part is. We need to find our up to find our gradient, don't we? So let's do our up calculation. Well, we've got, that's going to be the difference in our two y values. So here's the upper y value and here's the lower y value. And you can see what I can do here is just expand the brackets as we've done in the previous examples. And then I can start to regroup all the parts here, can't I? So it's this yellow part here, the x plus h squared here, is there in the upper point, and there's the x squared in the lower point. And there it is once we've expanded it. And then we can bring those two parts together, so I can bring that down there. And what we're left with, that yellow part, is the difference in heights due to the x squared, yeah? And then we can go on and we can have a look at the minus 4x. That's that sort of pink section here, yeah. And there are the two parts. That's the bit from the upper y, and that's the one for the lower point. And then again we can group those together. And there we have the part that relates to the second term, the minus 4x term. And finally, and of course that's going to be the gradient of a straight line is going to be linear, isn't it? We're going to find that in a sec. And the final part is our plus 4, isn't it? And what's the change in the plus 4? Well, there's actually no change, is there? There's our plus 4 in the upper point, there's the plus 4 in the lower, and when we group them together they cancel out and we get 0. Yeah, so that's our little up, our change in the up direction. And therefore if we now want to find the gradient, which is the up over the along, we've got our yellow section part of the expression, 2xh plus h squared there, that came from the x squared term, didn't it? And then we've got our minus 4h here, that came from the 4x term, and we've divided, then we're going to divide it by h, and therefore we end up with this expression. And as we did before, when we make this a very, very small triangle, our h value here effectively goes to 0. So what we end up with is an m value, our gradient here. Our gradient is going to be the 2x coming from our x squared term, and the minus 4 coming from our minus 4x term. Yeah, so can we see that in effect is our, let's just underline below then, so just very quickly looking at that, from our y we've got our x squared creates the 2x term, and our minus 4x creates the minus 4 in our gradient, and the plus 3, plus 4 rather, well that's constant throughout, so it has no effect on the gradient, doesn't it? That's like having a flat line. Yeah. So can we see that we could have done this as separate parts, and let's just convince ourselves of that. So if we take the part which is the y equals x squared, so y equals x squared, there we go, we would get that gradient part there, wouldn't we, the 2x from the differential. If we had the y equals minus 4x, we'd get the minus 4 part. And if we've got just a plus 4, we're going to get 0. And if we just add those parts up, there we go. We get a 2x minus 4 there. Yeah. So in practice, we could have done this, use the formula we've got, a generalized formula, and just done the parts separately. Yeah. Okay. So to summarize, if we've got a polynomial and we want to differentiate it, then the differential will be the sum of the differentials of each of the parts separately. We know what our generalized formula is here, then we about y equals x to the n, and the differential, the gradient of that, is going to be n x to the n minus 1. So if we had a polynomial like the one at the bottom here, and generalized one, ax to the 3 plus bx squared plus cx plus d, then we can just differentiate each of these parts separately and we'll get the differential of the total. So we get our ax to the power 3, because it's just going to become, we can just go straight in and go 3x squared, and our bx squared is going to become 2bx, and our cx is going to become c, and our d differentiate is going to be 0. So there you are. We can just do it in parts.